folks, what's up? In this video we're going to see about how to actually implement dynamic programming solutions using the previous approach that we have discussed in the previous video. So if you haven't watched my previous video, I can always give an I button link. You can always watch them there. Now this video we're categorizing it to divide it into three sections. The first section will be including the recursive approach, to see and break the problem into a recursive solutions. And in the second part we'll be discussing how to detect actually what are the number of parameters that are changing in a subproblem or breaking of a function into a smaller subproblem, and then to detect what will be the size of the data structure that we're going to use to store the values of the recursive solutions. And in the third part we'll be seeing like how to use that approach to store into the data structure and actually get the value from the data structure without doing a repeated recursive call. So till then, if you're new to our channel, do hit like, share and subscribe. Till then, enjoy the video. So let's understand this dynamic programming approach or the problem using recursion. So in this case, I am considering Fibonacci, which is a very common problem that we first initially solve in order to solve any dynamic programming problem. So let's dive into it and see how it does. So as we know, like what Fibonacci actually means is that we need the previous two numbers in order to find the next number, right? So in order to find f2, I need because the sum of these twos is equivalent to f2. Similarly, for finding f3, we need f2 and f1. So this is what Fibonacci problem actually means, right? So now let's look into this recursive tree and let's see what it does. Now imagine like we have been asked to find the Fibonacci value of 5, right? So we don't know what is the value of 5. So what I'll do is I'll try to divide this into smaller subproblem. Let's say, as we discussed, right, we need the previous two numbers, so we are dividing into two. Like 5 is given back, if I subtract 1 from 5 it will be 4 and 2 will be 3, right? We need these two values to detect or find the value of f5, right? So we are first dividing into subproblems such as f4 and f3, right? Similarly, again, I don't know the value of f4. It will again divide it into f3 and f2. Similarly, I don't know the value for f3. It will again divide the value for f2 and f1. And gradually, when we come down to a certain level, we'll see that f2 is divided into f1 and f0. Now, this is the base condition that we have or we have been given, right? Because below that we can't really have two numbers that are lesser than a number and then we have to find that value. So at least we have a base condition where we need to stop our function's execution and return the value from, right? So this is the point in this case where we are expecting a base condition to be executed, and in this point we have the value for f1 and f0, right? So once we have the value of f1 and f0, we are going to add this and return it to f2. Similarly, f1 and f2 will be having their own values and it will return to f3. And similarly, f4 and f3 will have the values and it will return the value to f5, right? This is how the recursion is for the Fibonacci, and this is how we divide it into smaller subproblem. Now imagine a case where there is a condition where we don't know, like actually let's imagine a case in where there is nothing, like there will be only last two elements that will give the value of the next one. Let's say this value is n, right? We need to have the previous n values in order to devise the value of the next function, right? So what I'm trying to say is, let's say I have f3. Let's say in this case n's value is 3, so we'll need f2, f1 and f0 in order to detect the value of f3. So as we have seen in the previous case, like this f5, we need two previous values, so we are dividing this into two subproblem. Now in this case we need like three of the previous values in order to detect the value for f3. So what we'll do here, we'll be just doing like f5 should now be divided into 3, right? So it will be f4, f3, and f2, right? Similarly, f4 will be again divided into its 3, like f3, f2 and f1, right? And in this case we'll need a base condition here as well, right? So in this case we'll be having a base condition which will be like having their own values, and depending upon that we'll gradually increment or go from the bottom to the top in order to find the final solutions, right? I think at this point it is very clear for us to understand that depending upon what are the requirements of the current function we have, we are breaking down the problem, bigger problem, into that number of sub problem. As you can see here, we are dependent on the previous two values, so we are breaking it into two. Now in this case we are dependent upon 3, so we are breaking into 3, right? So this is how we actually divide a bigger problem into smaller sub problem using recursion, and we detect this that how many number of division it should be depending upon the use case it has or its dependency it has on the previous sub problem, right? I think up to this it is clear. Now if I talk about recursion, as you have seen here, it is three step process, right? We should first need to identify the base condition. In this case we already knew like f0 and f1 is equal to 1. There will be many cases where we will not know, actually there will be not given any base conditions. You can take the example of, let's say, a gold mine problem. In that condition you will need to figure out like what should be the base condition depending upon the problem statement. So the first thing is identify the base condition, like where the program should stop or execution, right? In the next step we'll be looking into like any operation or any value depending upon the problem. So in this case the operation is f1 plus f2 is equal to f3, this one, or in this case it was f2, f1 and f0. The addition of these three gives the result of this. So this is the operation that you need to perform in order to find the value, and this value is passed on to the next thing in order to get the value of the subtotal or the maximum value, right? This is how it works, and this is the second step that we are basically considering, that the operation, that any operation we want to perform, right? And in the third part we need to look into how our sub problem need to be, like how our bigger problem need to be divided into the sub problem. Like as we have discussed here, it depends on its dependencies, right? On what things it depend and how it should work. In this case we have two dependencies, we are dividing into two. Now in this case we had three here, so we needed three branches of it, like we need to have three sub problems for it, right? So this is what step number 3 justifies. So every recursion problem is basically divided into three parts. So first part is the base condition, identifying the base condition where the program will actually stop. The next part will be the operation that we want to perform. The third thing will be how we want the bigger problem to be divided into smaller sub problems. They are the basic three things. Like if I would show this to you, like this is how recursion look, right, for the Fibonacci. So let's see this. Like we are giving, like given an input of n, let's say in this case it was 5, right? So we are given an input of 5 and we need to detect the value of Fibonacci number of 5, right? So in this case we have a base condition that is given, like for f0 it is 0 and for f1 it is 1, right? So it is similar to this, like if n is equal to 1 then it will return 1, if it is 0 it is 0, right? And now we depend on which two values, it's previous two. So what will be the previous two? That will be n minus 1 and n minus 2. So this is what we do, like we are asking the function to get the value of this one, let's say it is v1, and get the value of the last second digit of the number that we are expecting currently, that is v2, and add this in order to get the value of f of n, right? This is how it works. And if I talk about these three approaches, where and how it is used, you can see here, like this is the base condition, right? This is the base condition, and this is the operation, right? This plus sign indicates the operation, right? And then these are the these are the two things that are the sub problem that we are dividing, that justifies the statement number 3. Like how many number of sub problem we want to divide. In this case we have divided into 2. So these three things are always there in a recursion, right? So this is how we actually approach a bigger problem and devise it into a recursive solutions and determine what are the number of subproblem it would have, and we determine what would be its operation on it and what would be its base condition as well. So I hope so. I think it is clear for you now. So now let's move into the next section. I think as of now we are well aware about how recursion works and how we need to divide our actual problem into a sub problem using the previous approach we decided. If you have any doubt, you can always ping me in the comments, and I will always try to reply you back as soon as possible. So now let's decide and see like what are the number of components that we need actually and to frame our data structure where we want to store our recursive calls value, right? So the next topic, as you all know, is determining the number of components. So what is that actually? So if I go back to the previous approach, you can see here, right, what are the number of components that are getting changed here. See, in the Fibonacci function we have only one parameter that is getting changed. In this case it is getting changed to n minus 1, and in this case it is getting changed into n minus 2. So what are the total number of parameters that are getting changed? That is only one, right? So we only need a 1D array in order to store these recursive calls value. We don't need a 2D array. So now let's go into a second solutions or a second approach. So just ignore this recursive case. It is one of the solution to unique path problem in the lead code. So it is a recursive function that is relevant to that question, so no need to worry about that, just understand the concept. Now we have two values here, I and j, right? So what it does is, you can see here easily, in the next time we call the function, it actually reduces I to minus 1, I minus 1, and again in the next function it reduces j to j minus 1. So let's now talk about what are the number of components that are getting changed. Number of components that are getting changed are I and j, right? You can see like in this function I is getting changed to I minus 1, and in this case j is getting changed to j minus 1. So there are total two variables that are getting changed. In this case number of things that are getting changed is 2. We know that, right? We can actually, as I think you should have known like how to guess that by seeing the recursive function itself. Like it should have a parameter which is getting reduced or incremented depending upon the problem, like how it is, how that variable is getting changed, and the number of variables that are getting changed on each subproblem will be contributed to the number of components that are getting changed as a whole, right? So it is not that like in one function it should have been two changes. Like it is not mandatory that this function will have I minus 1 as well as j minus 1, right? We can always have one function as I minus 1 and other is not changing, and other one is also having I and j minus 1, right? We don't need to have both of them, right, in the same function. So this is what I want to mean actually, like not to say, like we should look it as a global thing, and we need to see like in the number of subproblems that we divide our function into, what are the number of variables that are getting changed. In this case it is 2, and similarly we can devise it for other recursive functions as well, right? Okay, so now depending upon the number of variables that are getting changed, we need to make that dimension of the array, right? So it is 2, so we need to make a 2 cross 2 array. In this case, sorry, not 2 cross 2 array, I mean like it's a 2D array, it's a dimension, sorry, it's a dimension, so it's a 2D array, right? And in this case, as only one of the components is getting changed, so it is a 1D array. Now we know that it is a 2D array, right? But what will be the size of the 2D array? So now you can see like in this, like it is I is getting started from m minus 1 and j is getting started from n minus 1, and it is reducing itself and going up to 0, right? And in 0 we have a base condition here, that is it is returning, right? So like in this case we have a 2D array where I, if I'm considering this part as I and this part as j, I is going from 0 to m minus 1 and j is going from 0 to n minus 1, right? So what will be the size of the array? So this will be 0 to m minus 1 is m, and 0 to n minus 1 is n. So the array size will be m cross n, right? Similarly, in the previous case, we had like n, right? Only one value, so we had a 1D array, right? Now you can see like n is a given value input that we get, right? And n is getting reduced each time and is getting finally arriving at n equal to 0, right? So it is starting from n and it is going to 0. So we need a value of n plus 1 in order to get the value of dp of n, right? So from 0 to n we need a length of n plus 1. So we need an array size of n plus 1 here. So it will be 1 cross n plus 1 matrix, right? This will be the size of the matrix. This is how we actually calculate the size of the data structure that we're going to use depending on the number of parameters that is getting changed on every subproblem we call in the recursive function. I hope this is clear. Now let's move into the next section. So as of now we are already good with the recursive calls, how we want to divide our bigger problem into subproblems, and we are also good to go with determining the size of the data structure that we want and to solve the value and store the value of the recursions in that data structure, right? So now the third topic is like how we can actually use that data structure to optimize the recursion and store the calculated value, right? So now let's go to the previous example itself. We have discussed that the size of this array will be m cross n, right? Now you can always see like this unique path function has a 2D vector or array that is defined with a value of m and n, right, which is equivalent to m cross n that we have already discussed, that this will be the size, right? Now after defining it, it is a sort of minus 1 here. So I am telling you why it is a minus 1. See, like we need to actually check in that data structure, right? In that data structure, that actually if that value already exists in that data structure or not. So we need to give or initialize our vector with such a value that wouldn't be a value with the solution of our bigger problem. So what I mean is like we should actually give a value or initialize the value that shouldn't be actually a solution to any of the recursion functions, right? What I mean by that is see here in this case the value will always be positive, right? So if I'm giving a negative value here and initializing it, I can guarantee that the if that cell is having a negative value, that means that recursive function hasn't been solved yet, right? If at all that value is not negative, then I can surely say that that function or that recursive function has been solved and the value has been stored in that particular cell, right? But if there is a value of minus 1, I can definitely say that that recursion function hasn't been solved, right? Okay, so now in this case we are giving a value of minus 1, but there can be cases where we can also have negative values. So in that case how we can manage that, that is a big thing to look into. So that things need to be done with practice only, so we can actually use that concept do that. So the, like even if I give a brief overview over that, let's say like we have recursive functions that have negative values. So there might be a case of minus infinity, let's say, where we can initialize our value to, right? In what do you say, in C++ it is int min, we say it is int min, right? Or it can be int max as well. Depending on the problem we can actually initialize our like data structures value, right? Or in many case actually if we are not sure about like what would be the value that we want to initialize for that vector or that array or the data structure, we actually use a map is better. Why I'm saying you, because if you don't actually find that whether like maybe there is a case where that value might occur, so you can use a map always. How you can use a map? You need to create a unique key. So let's say here I and j is there, so I can just do something like I concat it with a hash, right, and then concat it with a j, and this will be a string, right, the key will be a string. So let's say 1 hash 1 is a string, right, 1 hash 2 is a string, which is another key to the map, and this way you can store the key, right, and this way you can always check like if this key already exists. Now let's say again my recursive function calls for 1 and 2. I can convert that 1 and 2 into this string, right, 1 and 2, and I can check like if this key already exists in the map. So if it exists, I can directly return from there, and if it not, I can guarantee that that recursive function hasn't been called yet. So these are basically two of the approaches that we generally use in order to store the value or retrieve the value. Most of the cases we use like these 2D vectors or the 1D vector, depending upon the size or size of the array or the dimension that we get from the number of variables that are getting changed here, that we have discussed already in the previous section, right. So this is how we do it. Now let's come back here. Now here we can see like this dp array is initialized into a value of m cross n with -1. We have discussed why it is -1, right. Now let's go into this. Now you can see like it is checking like if dp of I of j is not equal to -1. I have already told you like if it is not equal to -1, that means that recursive function is already been calculated, right, and it has already been solved. So we not need to solve again and again. So you can just directly return it from here. Whatever the value that is stored here, you can just directly return it from here. But if it is not solved yet, then we again go for its subproblem and we ask the function that you solve this for me, and once that thing is solved, we store that in that cell, right, we store that value in that cell, as you can see it here. So once I get the value for left and right, I am trying to store it in dp of I of j, because as of now dp of I of j is having a value of -1, because if it would have a value of not -1, like if it doesn't have a value of -1, then it would have already returned it from here. But as it doesn't has a value of like other than -1, right, so it is actually having a value of -1, so we can guarantee that this function hasn't been solved. So we recursively call for its subproblem to solve, and once we get the value, that is this up and left, we store that value in that cell itself, so that next time we have a call for that particular cell, we don't have to call it subproblem again and again. We can just directly return from that cell itself, right. So this is how we actually devise size of the data structure, and then we store and check whether that value is already computed and stored in that cell or not. So if it is stored, we can directly return from here, as in this case. If not, we'll have to compute for its subproblem and we store it in that cell actually. So this is how the TP problem is actually solved or approached and implemented. So till now we have discussed a hell lot of things. So first one, how to approach a dynamic programming problem and divide it into a recursive solutions, how to decide like what will be the number of subproblems a recursive function should have, and then coming back to the next part, we have also discussed like what will be the size of the data structure, what will be its dimension, right, and the next part, how we actually implement or store the value in that data structure and retrieve it. So hope you guys learned a lot. In the next video, we're going to see about how to actually implement this using the help of the core basic standard DP problems that we need to solve in order to gain our confidence as well as a better concept on the dynamic programming problems. So till then, stay safe, stay tuned. I'll see you in the next video.